Still muted, John.
I'm unmuted.
There
How
you
much money do I have to put in the swear jar? In the muted jar. Does anybody here remember Eric Clapton with an afro?
No, I don't.
Before my time.
Yeah, I don't remember him. I always remember him just as the beard and the hair, but not like that. That's Cream. Okay, that's our thing. That's our theme for tonight, man. And that's a great tune. That's a great tune. Welcome back, everybody, to the show that never ends. All right, we are so glad you could attend. Let me get the right screen up here for you, here, people. And there we go. All right. Is everybody happy?
Ecstatic, my man. Ecstatic.
Everybody's happy.
Welcome to Takeo After Dark Part 3. John Barber here with Jason Cox, Dave Holdorf, and a word from our sponsor, John Messenbrink. How you doing, guys?
Awesome, dude. How you doing?
I tell you what, I see you wearing the Bears cap there. I got to believe you're happy with the results of the weekend.
Yeah, it was better than average, I'd say. It's no Abdul Carter.
There you go.
Come on.
Well, hey, you got some players. Very happy with what the Patriots did.
Yeah.
Okay. The Jets, well, they jetted it up, and that's great. I'm happy for them. And I don't know, who do you follow, Jason, for football?
I'm a Minnesota Vikings fan, and we got a guard as our first pick, and I think we traded a couple of picks, so I didn't follow it after the third round or so.
Yeah,
we got a good
being
strong
a cream from Northern California. Being this Northern California, I could see the Vikings connection.
Well, no, my dad and my dad's side of the family is all from Minnesota.
Yeah.
So
there you go.
It's a curse that I inherited.
Hey, listen, Vikings fans and pre-2004 Red Sox fans were brothers from another mother. Just join at the hip.
That's right.
But when you win, it's going to feel really good. I'll tell you what.
Yeah.
Mr. Messenbrink from our co-sponsor, mechanicalhub.com.
Yeah.
Tell our friends out there what mechanicalhub.com is, and if they haven't heard yet, what can they find on the website this week?
Online resource, mechanicalhub.com, plumbingperspective.com. A couple of weeks ago, I don't know, maybe a month ago, there was a story in Louisiana of a plumber who died in a tunneling accident. He was underneath a house.
Oh my.
And so I did a little research and got some information from OSHA. So I have a story on tunneling and shoring and shielding and all that good stuff, trenching and all that good stuff on the site this week. So it's pretty good. Pretty good.
Yeah, if you've ever been in a ditch or anything like that starts to cave in, that's scary as hell.
Yeah.
That's scary stuff, because you're at the mercy of nature at that point.
Yeah, I don't know how these guys do it, especially when they're like, hey, go on in there, and it's not protected. There's no, there's no trenching involved. There's nothing. Just go in the pit and cross your fingers. So
right, it's like what could go wrong? We've done this 100 times.
Yeah,
it only takes once, man. It only takes once. Well, I have more cheerier stuff. What tonight is part 3 of Takeo After Dark. Let's do a quick roll call, really quick. We've got Jason, we've got Dave, we've got John, we've got the other John. Chime in from where you're at. Go down to your chat section on your control panel, and if you would please, I know a few guys have got it already, but just say hi, hello, how you doing, and where are you from, man? We got a Montana. All right, Kevin's from Montana. Excellent. America's Roller Coast. That's from Todd. I don't know where that is. Where is America's Roller Coast? We only have 3, so I'm not sure which one it could be, but that's all right. Okay, we got Orlando, Sandusky, Ohio, Michigan, Cedar Point, Wyoming, Canton, Ohio. Great. One of my favorite towns, Canton, Ohio. Pro Football Hall of Fame. What a lot of fun. What a lot of fun it is.
By the way, I'm not brown nosing, am I? Look at this.
A little bit, John. A little bit.
Oh, that reminds me. Yeah, I'm gonna get mine filled.
There you go. Oh,
there
whoa.
Whoa. Hey, it's Takeo After Dark, man. I'm home.
There you go. And the smoking lamp has officially been lit. I tell you.
Is that Jefferson? What is that?
This is Redemption Bourbon.
Oh, Redemption.
Oh, wow.
Okay.
Yeah.
Smooth.
So I got to get myself a nice healthy pour. Got the big old golf ball ice cube in there too.
Wow.
Mercy.
Sure.
Well, all right. Again, welcome
And,
to.
and so while you asked everybody where they're from, right now we got to go find out what everybody's drinking tonight and come joining us with.
Oh, well, there you go. Yeah. Hey, there's another thing.
That is one of our rules.
That is one of the rules. So chime in, folks. What adult
What do
beverage do you have in front of you?
Unless you're on the West Coast and you might still be in the office.
You might still be in the office. That's right.
This adult
You still
beverage
could be
is
drinking,
water
you
for
know.
me today, brought to you by Niagara.
There you go. There we go. We got coffee, iced tea, and coffee. I just finished some Polar sparkling water, Trader Joe's sparkling water with lime. I may have to go out and get another one, but that's all right.
Hey, real quick.
We got a Yingling. All right, good. Yes, John.
Dave, do you drink whiskey? I mean, are you well versed in whiskey, or are you just kind of for fun, or how?
No, I started obviously during Takeaway After Dark.
Oh, okay.
So and exploring and finding the ones I like. So more or less. No, I couldn't tell you. I'm not going to sit here and have a half-hour conversation with you on different bourbons.
Oh, because I was thinking about doing an IG live like once a month on whiskey. So you might be a guest one time. So
all right. Do I get to try and taste?
Sure.
Right.
Remotely, yeah. Anyway, sorry about that.
Excuse me, could I have control of the show back now? We'll talk about whiskey later, all right? Tonight's topic, we're going to talk about pipe sizing, air control, and that funky little doodad called pumping away. One of those things that I still don't believe is fully understood. A lot of folks think they know what pumping away is, but the more you ask about it, people read about 2/3 of Dan Holohan's book. They didn't finish it. Okay, there's a lot of stuff to understand here, and we're going to talk about that as well tonight. So that's on the agenda this evening. So I want to make sure everybody's ready. This is part 3 of 9. So we've got after this one, we got 6 more to go. Look out for tomorrow night's email. Right about this time, you will be getting an email from us with your certificate of attendance, which is officially mandated and all that. That's good. And you'll get a link to the recording of this presentation, and you can watch that and share that as much as you want. There's no limitations on that. We're not allowed, obviously, to give out our PowerPoint, unfortunately, but you have that recording for you as well. So look out for that tomorrow. We will have prizes for participation where you've got a trivia question. We like to give away prizes just for people who participate and, work with us a little bit, because I don't know about you guys, but I'm not the most interesting person on the planet. I think well, you probably will all agree enthusiastically with that statement. These things get, if it's just me droning on or Jason droning on or Dave droning on for an hour, they get pretty boring. All right. What really makes these things sing is your participation. So ask questions. So I'm glad all you folks out there know how to use that question section, and please ask your questions as we go along. We'll be taking breaks every few slides to just go over some questions. Jason and Dave will be paying attention to the chat window there, and they will be answering questions directly as well. So we want to make sure everybody's questions get answered, but please ask those questions, and we'll stay on as long as y'all want to at the end, and we can talk about anything you want at that point. Any questions that have been driving you up a tree about TACO, about hydronics, about heating or whatever, we'll stay on as long as y'all want to. So that comes up, and there are prizes for that thing. Dave, what prize? We still have the backpack / cooler.
The backpack coolers, yes, I still have a supply of those. They should make it to the end of the semester, end of the sessions. Yes, I have enough of those to make us to the end, as well as some Takeaway After Dark t-shirts. So yes, the cooler backpack, I believe, can fit at least a 12-pack, if I'm correct, on bottles, or at least 6 bottles of wine, I think, can fit in there too. I don't know how I know those numbers. I'm not sure.
How many bottles of bourbon?
It depends. I like to keep mine bubble wrapped and stuff, so maybe 2.
Okay. And in case you haven't noticed yet, the name of the game is fun here. Let's have some fun. We're not taking this too seriously. Let's enjoy yourselves. Let's have some fun and enjoy this. Enjoy the time we get together to spend together tonight. It's a special time. So let's have some fun and make it all worthwhile. Tonight's cast of characters, tonight's theme, you may have picked up from our theme song, Strange Brew. Tonight's theme is Cream, one of my favorite power trios of the 60s. They were a bright shining light for just a few years, and then they went their separate ways. You had Ginger Baker on drums, Jack Bruce on bass, and Eric Clapton on guitar. I mean, these guys were hot, man. They were the epitome of the power trio, which I'm trying to recreate with myself, Jason, and Dave. Okay, it's just we're trying to recreate that power trio. None of us have any musical ability. That's the problem. Okay. So I don't know what we're going to be a power trio of, but maybe we can play kazoo or something. I'm not sure.
You guys can sing. Come on.
No, we can't. I've heard all of us sing. No, we can't, John. No, we can't.
No, I was one of those people, you know, you always look for the bad karaoke singers, right? I was asked not to do it again. Yeah.
Yeah.
I was done it once, and John was present for that one, and I was asked to not do it again. Yeah.
Oh God, no. Jeez.
Wow.
Yeah.
It was painful. It wasn't even funny to watch. It was just painful to watch.
All you need to know, I was in a musical in high school. I had the only non-singing part.
Ah.
So there you go.
Jason?
Anyway, creamsicles, my creamsicle friends. Let's get this thing rolling, and we'll talk the talk and walk the walk about hydronics. So where did we leave off last week? We had another BAFO session last week. Dave wasn't here, but that's all right. We muddled through without you, Dave. But where did we leave off last week? Well, we talked about a bunch of things. We talked about, you know, the finer points of fin2 baseboard, okay, 180 or 170. Which temperature column do we use? If it's average water temperature and the water's going out of 180, come back at 160, you got to use that 170 line. 1 gallon per minute or 4 gallon per minute flow rate. What's the output at both of those? You got to pick 1 gallon a minute unless you absolutely know what it is. So there's some interesting things to learn there. We talked about that. We talked about cast iron radiators and panel radiators, and how to figure out the BTU output of those based on different water temperatures. And we got into some detail there. We got into a deeper discussion on radiant floor heating and the different installation methods and the unique thing about surface temperature, okay? It's surface temperature is what gives off the BTUs, not the pipe or anything else. It's all part of it, but the surface temperature is the important thing. And then we talked about boiler ratings, the AHRI/IBR ratings versus the DOE rating. So that was all part of last week, and I thought it was a pretty good session. I hope you all did too if you were there. We're going to start off talking about flow rates and how that impacts pipe sizing, and both of those will impact head loss or pressure loss, which we'll talk about next week. And we're going to talk about pumping away. Where does the circulator go? All right. It's important to understand about hydronics is that we're talking about math, man, right? This is all math, right? As much as well, let me take a poll real quick. Just type in if you would. How many of you hate math or believe you suck at math? I'm curious. I'm sure we have some engineers out there, and then this stuff is your life. But who here hates math and sucks at it? Believes that they suck at it? Eugene, good for you. Put Eugene in the prize list. He was the first honest guy here. He jumped in and said, "I do." So yeah, we tend to, in our industry, we do believe. I've talked to so many people. Whenever I talk about math, you see the body language guys go, "Oh," and they slump and they said, "Oh, man, I hate math. I hate math. I suck at math. I hate math." I gotta believe. I'm going to suggest this to you. I believe anybody who answered that they're not their best subject or hate math or whatever, I believe you're better at math than you think you are. And here's why. When they taught you math starting in first grade all the way through 12th grade, when they taught you math in school, did they really give a crap what X was? What were they trying to teach you? What do you think they were trying to teach you? They were trying to teach you the process. Systematic, logical, problem solving. Yeah, William, you got it. It's a way to think, and it's a way to solve problems. If any of us out there listening absolutely love, and I'm getting an echo here, guys. I don't know if one of you got a speaker on. If someone could turn your speaker down, and I won't get. Okay, there we go. Oh, no, still got it. All right. Anyway. Yeah, it's how to get an answer, right? But if you like to troubleshoot, walk into a system and try to diagnose what's wrong with it, that is systematic logical problem solving. That is from your math background. right? That's from your math background. So you're better at it than you think. And there isn't, because hydronics is a science, we're talking about BTUs and all that stuff with heat loss that we did, that was math. That was addition, subtraction, multiplication, division. That was easy stuff, right? But that was all math. There's only one math formula, I believe, that you need to know stone cold, meaning memorized. You know it as certainly as with the same amount of certainty that you know your name and address. That's how important it is. This math formula, the universal hydronics formula, is as important to our profession as torts are to a lawyer or anatomy is to a doctor. All right. You don't want to go to a doctor who says, wait a minute, I got to look up where the larynx is, you know, where's the spleen again? Let me check the book, you know, give me a rule of thumb on how to take out an appendix. You don't want that doctor, right? You don't want that doctor. You want them to know. Same thing with us. We got to know this formula, the universal hydronics formula, and it's a simple one. It states quite simply that GPM is equal to BTUH divided by the product of delta T times 500. All right, let's identify the terms here. GPM is the gallons per minute flow rate that you need to deliver the BTUH required. Okay, it's how many gallons per minute do I have to pump through this pipe to deliver, at what flow rate do I have to pump to deliver the BTUs required for whatever it is I'm pumping through. So that's GPM, gallons per minute. That's our pulse. That's what we need to find. Okay, BTUH, of course, that's the BTUs required. That we figured that out in our heat load section earlier in part 1. Delta T, we talked about that also last week. Delta T is the designed for, keywords here, designed for temperature drop of the fluid as it goes through the piping circuit. Typical residential hydronics, we design to a delta T of 20, meaning that water might go out at 180, come back at 160. We have an average water temperature of 170. We do residential radiant, often the delta T there is 10, you know, especially for between the joist applications and things like that, our drier applications. We want nice, consistent floor surface temperatures, all right? So that we would use a delta T of 10. So water goes out at 120, comes back at 110. My average water temperature is 115, okay? So that's the delta T. We choose that. And then lastly, we have 500. Now, 500 is a mathematical shortcut. 500 is a rule of thumb, so to speak. 500 is a number, a multiplier that we use when we have 100% water, 100% water at room temperature, all right? And where does that number come from? Well, it comes from multiplying the weight of 1 gallon of water. 1 gallon of water weighs 8.33 pounds. We multiply that number by 60 minutes in an hour, all right? The number of minutes in an hour. Most parts of the country, that's 60. You know, I don't know about Northern California, Jason, you know, it's a little slower there.
How did I know that was coming?
So 8.33 times 60 times 1 times 1. What are those ones all about? Well, the first one is the specific gravity of fluid. 100% water has a specific gravity of 1. The second one is the specific heat of fluid. 100% water has a specific heat of 1, in that it takes 1 BTU to raise 1 pound of water, 1 degree Fahrenheit, 1 hour. That's a lot of ones, man. That's a lot of ones. So 8.33 times 60 times 1 is 499.8. We'll call it 500. What's 2/10 of a degree between friends, right? What happens when you throw glycol into the mix? Anybody know? You guys out there in webinar land, what happens when you throw glycol into the mix? Tick tock, tick tock, tick tock, tick tock, tick tock. Changes. Yes, it does. Thank you. Yes, it changes. Very good. It changes. It changes. What it does is glycol doesn't weigh the same as water. It doesn't have the same specific gravity. It doesn't have the same specific heat. Other than that, it's the same. Okay. So it changes everything except the 60 minutes in an hour. Okay. It's more viscous. It doesn't transfer heat as well. So depending upon your water to glycol mix, that 500 is going to change. It's going to go down. All right. Some of the already mixed glycol, if you look at the jug, Cryotech 100 is the one I keep in my head. If you look at the jug, it says use 493. All right, that's pretty close, but the lower that number, the higher the flow rate you're going to need to deliver the same amount of BTUs. You start getting into the stuff you mix on site, a 30-degree glycol, 70 or 30% glycol, 70% water mixture. That number might go down to maybe 475. You do a 50-50 glycol mix like you would do for snowmelt. Now you're talking maybe a 435 multiplier. Okay. The thing is with glycol, there's no universal standard. You got to look at the jug, man. You got to look at the jug of what you're using and interpolate the math there, because it can matter. The more glycol you put in, all right, the more glycol you put in, the higher flow rate you're going to need to deliver the BTUs. And as the flow rate goes up, the pressure loss or the head loss through the piping is going to go up as well. So those are all things that you got to keep in mind.
Yep. I'll also add one other thing in there too. When you are looking at what concentration you want to put into your project, pay attention to what what the equipment says, the glycol that you're getting in, because it'll say that percentage, and I'm just going to make up a number. Let's say 25% is going to get you to say a 10-degree temperature. Now, the one thing you want to remember there, it's not the air temperature that you're looking at. You're looking at fluid temperature, right? So that's what they're trying to tell you for your protection. Your protection says, all right, 25% is going to get you that fluid to 10 degrees before ice crystals start to form in the water. It doesn't mean it turns into a block of ice at that point. So when we're putting in antifreeze glycol into our systems, also think about where you are in the country. And like, for example, here on Long Island, I know we want to do it because what if we lost power? All right. And, we're not going to be able to move any water. We can't fire off the boiler, stuff like that. How long are you without power? Right? Will the fluid in your system get to 10 degrees? I know on Long Island, I lose power for more than an hour. Long Island everybody's lost it. Right? They're getting power back again. We'll run across the pond and get to Connecticut with extension cords. So, to get electricity back on Long Island. So we don't lose power for a long period of time. So just think about how much that concentration is when you're putting it into a project.
There you go. Yeah, good. Excellent point. We had a question from Ryan Moore about Sentinel fluid 100X or 400X. I guess boiler water treatment chemicals. I don't believe they changed this formula much. I don't think they changed the viscosity much. You'd have to check the canister of the stuff that you put in and see what it says, but I don't believe it changes it very much. All righty, so let's do one here. Let's do a little example. All right. So here's our universal hydronics formula. And let's say I'm trying to size the pipe for a 25,000 BTU zone, baseboard, radiators, radiant, whatever it is, we're using a 20-degree delta T here. We're going to use a 20-degree delta T. So I just start filling in what I know. GPM, I don't know that. I know the BTUH, that's 25,000. I know the delta T, that's 20. The 500's already there. Now it's simple math, all right? 20 times 500 is 10,000. One of the cool things about a 20-degree delta T is it gives you 10,000. You can divide anything by 10,000. That's pretty easy. So if I take a look at this, 25,000 divided by 10,000, my flow rate is 2.5 gallons a minute, 2.5 GPM. That's what I need to deliver 25,000 BTUs under design conditions. All right. Now, if it's 50% load, I've got 12,500 BTUs. Now I would really only need 1.25 GPM at that point. This brings up a bunch of other things that we'll talk about next week when we get into circulator sizing. But just keep in mind that 2.5 isn't stagnant. It's our goal under design conditions. Okay. Excellent. Now that brings us to pipe sizing guidelines. How about that? Flow determines what our pipe size needs to be. All right, and these are very general, very safe guidelines. All right, you can get into some of the finer points and you have some leeway here, but these are very safe and basic. If my flow rate is 2 to 4 GPM, and we're talking copper here, PEX, look at the PEX manufacturers, but 2 to 4 GPM, that's going to be 3/4 inch type M copper, type L copper. All right, 2 to 4 GPM. If I'm 4.1 to 9 GPM, that's generally speaking 1 inch pipe. All right. 8 to 14 is 1.25 inches. There's an overlap there I'll explain in a second, okay? But 8 to 14 GPM, we're looking at 1.25 inches, all right? And then 14 to 22 GPM, we're talking about 1.5 inches. And then you go up from there, but these are just some basic residential guidelines. 2 to 4 GPM, 3/4, 4 to 9, 1 inch, 8 to 14, 1.25 inches, 14 to 22, 1.5 inches. The reason these guidelines are the guidelines has to do with minimum and maximum fluid velocity. All right. How is velocity different from flow rate? Well, flow rate, gallons per minute, that's, if you think about a road, that's how many cars are on the road at one time, moving down the road at one time. All right, gallons per minute. Velocity is the speed. All right, how fast are they going? All right, how fast are all these cars going? So the minimum fluid velocity we're looking for in a closed loop hydronic system is about 2 feet per second. That's the lowest velocity we're looking for. The highest velocity we're looking for is right around 4 feet per second. Now, let me ask the group here, and please type in your response because I'm interested in hearing what you guys think. Is it possible for me, if I put a pump big enough on this, can I push 22 gallons a minute through a 3/4 inch pipe? I'll tell you right now, I sure as hell can. Yes, we make a pump that'll do that. You absolutely can. My question actually should be, why would you not want to? What would be the problem if you did? Okay. What would be the problem if you did pump 22 gallons a minute through a 3/4 inch copper pipe in a closed loop hydronic system? Type in your thoughts here. All right. We got a couple. Very good. We got some good ones here. All right. Excellent. Now pressure loss. A lot of people said pressure loss. I'll say no, because in order to put 22 gallons a minute through that pipe, I'm going to need a high head pump. All right. We make pumps that'll do that. It's not the head pressure or the high head loss isn't the problem. It's just something we have to overcome, and we can do that. Okay. We have pinhole leaks. We have velocity noise. Those are the two ones. Early on, someone said pipe erosion. We can, at those velocities, we can start to erode the pipe from the inside out. Water's the universal solvent here, friends, and that will erode the pipe from the inside out. The place you're going to see it first are in changes of direction, fittings, where the water goes bam and goes that way. That's where you're going to see that turbulent flow. That's where that's going to be. That's where it's going to show up first. Okay, that's where it's going to show up first. Hopefully, someone complains about the velocity noise before you get to a pinhole leak. Because I'll tell you what,
it's going to be a hell of a lot noisier. Yeah, you're going to be hearing that whooshing through the pipes.
22 gallons a minute through a 3/4 inch pipe. It's going to sound like a freaking freight train going through the house. Okay, someone's going to raise that alarm first. Okay, they're going to raise that alarm first. Someone mentioned earlier about I saw this thing about you're not going to be able to give off heat. Well, as long as you have a delta T, you're giving off BTUs. GPM equals BTUH divided by delta T times 500. As long as there's a delta T there, you're going to get those BTUs. Not optimal. The small delta T's have another problem. Again, we'll talk about next week. But that's the issue with more than 4 feet per second. My other question now is, what happens if the velocity is less than 2 feet per second? What happens if can I put 2 gallons a minute through an 1.5 inch pipe? I can do that all day without breaking a sweat. I don't even need a circulator. Just put a hamster on one of them running wheels and they'll move the water through, right, at that point. But why don't I want to do 2 gallons a minute through an 1.5 inch pipe? What would be the problem there? Now type in your answer there and we'll see what we got. Now I can't really overheat the water. Again, we're still moving it. Okay, delta T might be high, maybe. But there's another issue here. Bingo, we got it. Ashley's got it. What you have is at velocities that low, velocities less than 2 feet per second, dissolved gases in the fluid have a tendency to come out of solution and turn back into bubbles. And now we have a noise issue of a different flavor. We have a babbling brook sound. We might have air issues. There are places within the system where we want to go below 2 feet per second to release those bubbles from their captivity, okay? But the distribution piping isn't one of them, okay? Distribution piping isn't one of them. So we got cavitation. Cavitation's a different animal, and it's almost impossible to have happen in residential applications. That's low net positive suction head into a large pump. The little ones we use, very, very difficult to have that happen. So it's a matter of those dissolved gases come out of solution and we have a babbling brook issue. Excellent. Very good. Very good. So we size our pipe. When we go about sizing our pipe, we use these guidelines. Let's talk about boilers for a minute. If you're like a modulating condensing boiler, sizing the legs out of the ModCon boiler into the header, that's easy. Okay. You look at the instruction sheet, they'll tell you. Okay. And what's the coolest thing about an instruction sheet, Jason? Do you know?
Well, I don't use them typically, but
They're free.
they're free.
They're free, and they're in every box, man. They're in every box. What did we say first class? RTFM. Read the free manual.
Yep.
Okay. It is it's a factory manual. Either way. But there's a wealth of information in the manual. There's a wealth of information in the manual. In this case, it tells you the water connection sizes, supply and return, 1.25 inches. Doesn't get much easier than that. Okay. You want to take some of the thinking out of this? Read the instructions, right? Read the instructions. Is that right? Now about the header, about this piece here. Now, a lot of times you see this is a Navion. Well, they will fabricate this for you, and you just buy it, bang, and you're done. Okay, and it's sized for that specific boiler, and I think that's cool. That's cool. Now, if let's say I have my distribution load is 127,000 BTUs, not the output of the boiler. This is the actual heat load of the structure. All right. And it's a 20-degree delta T, 127. This big honking house. All right. We're up in the mountains. It's, it's the kind of the shower where you and 14 of your closest friends can all bathe together. I mean, it's that kind of a place. All right. We have 127,000 BTUs divided by 20 times 500 or 10. Now we're talking about a flow rate of 12.7 GPM. If we're going to I turned off the webcams. We had a slow connection here somewhere. If we're going to size according to the load, 12.7 GPM, that's going to be 1.25 inch header based on our guidelines, 1.25 inch header. And that's cool. That's all right. You don't want to undersize a header, but it's okay actually if you understand the job of a header. If you understand the job of a header, it is okay to oversize it because the job of a header is hydraulic isolation. And we'll have a session on that a little bit later on as well. But oversizing that header is not really a problem. And actually, there's some benefits to it. So if you wanted to go 1.5 inches, you certainly could. You certainly could. Alrighty, very good, very good. Now, what's next? We're going to talk about this little package right here, okay, on the supply. In this example, we're looking at the pressure reducing valve, all right, the pressure reducing valve, the air eliminator, and the expansion tank. Pressure reducing valve, air eliminator, and the expansion tank. One product I want to share with you because this is such a cool product, and I think it's very underutilized and underappreciated. But this is the Taco 3450 combi valve. This is a pressure reducing valve and backflow preventer in one unit, one package. You can buy them, like the Watson. We have them as well. Taco has them as well, where you've got your standard backflow preventer, your standard pressure reducing valve, and we package them. We connect them and put them in a box. This is different, and this is one piece. This is a one-piece, single-piece unit combi valve. So it has both. It's serviceable. Okay. The footprint, the water footprint is actually the exact same as a standard pressure reducing valve. So it takes up a little bit less space. That green extension you see there is actually a gauge to tell you what you have set the pressure reducing valve for. Most pressure reducing valves, you're taking a wild ass guess, right? This actually will show you what you have it set for. Those dials on the end will allow you to adjust your pressure setting. It comes factory set at 12, but you can adjust it if you need to. That little button on the end is fast fill. And here's a cool element of that unit. When you're filling up the boiler or purging, all right, you press that button and it stays in the fast fill mode. Okay, then you go and you open up your valve, right, and you blow the air out of a loop, and then you close the valve. Now I'm going to ask a question to this group, and I want an honest answer from everybody out there. I know it's happened to everybody here at least once. How many of you have not got back to the old style pressure reducing valve, the kind with a lever? All right, how many of you have not gotten back to that lever in time to close it, take it out of fast fill before the pressure relief valve blew up. Okay, Dave Cooper, Dave Holdorf put Dave Cooper in our prize circle. He's the first honest guy. Yeah, everybody. That happens to everybody. Everybody's, oh, it never happened to me. Yeah, right. It happens to everybody, and you feel silly. All right. Usually it would happen to me before I piped the downspout into the for the relief valve, and it just blows everywhere. And I feel like and then you walk around, I feel like a schmuck for the rest of the day. But what this one will do, all right, is when you close the valve and we get right back up to 12 psi, pop, it closes itself. You don't have to touch it. Okay, it does it on its own. I think that's a pretty cool feature. All right, again, underappreciated, underutilized, but an awesome little valve. Also, I don't know how many of you know this, but Taco does sell boiler trim kits. Okay, so you've got these 3 different options that you see in front of you here. That all the parts you need are in one box. All right, and then you've got the nipples, the fittings, everything. You just put them all together, and it's all in a trim kit with the expansion tank as well. It's got everything in there. I want to direct.
John, I hate to interrupt you, but as a former wholesaler, I just love this concept so much. You know, you have one SKU on the shelf versus having your air separator, your backflow device, your autofill. It's just great to be able to pick up one box and one SKU and pay one price. Right?
There you go. Absolutely.
Yeah. How many times have you forgotten a T?
Mhm.
Oh crap! I don't have a 3.5-inch nipple now. Yeah, exactly.
Right. There you go.
Got to take a run back.
And on the kit with John, you're circling it now. I'll let you go right ahead.
There you go. This guy right here is important. This is a little drain and isolation valve.
That's a beautiful thing right there, Dave.
Yeah. If you think about it, the manufacturer of expansion tank will tell you that the bladder is not airtight. All right. It will, through the magic of oxygen diffusion, that you can lose up to 1 psi annually on the air side of that expansion tank. And as you start to lose pressure on the expansion tank becomes effectively a smaller tank. Okay, less acceptance volume. And then you reach a point where at some point you blow a relief valve. So they recommend checking them every year for air pressure. The thing is, you can't check them for air pressure when there's water pressure on the other side. So without an isolation valve like that, you can't do it. You got to drain the system, take the tank off, get the water out, check the pressure, put it back on, then refill and repurge the system, which is a pain in the neck. What this little valve here does, the first yellow valve isolates the expansion tank from the rest of the system. The second yellow valve, you put a hose on the end there, basically lets you force out whatever water's in the expansion tank. Now there's no water pressure in the expansion tank. You can accurately check the pressure charge on that. So that's why that little double yellow handle is solid gold, man. They should be on every job. Absolutely should be on every job.
Of course, check code, because there are some places in the country that don't allow that valve on your expansion tank.
It's only if you ask. All right.
Oh, really? Is
that only if you ask?
What would they say, Dave? Just a full port ball valve instead of that particular valve?
No isolation whatsoever on the expansion tank.
Oh, okay. I'm not running into
because when that expansion tank starts leaking, and a homeowner goes walking downstairs and they say, "Oh, well, if I shut that valve, the leak stops."
Yep. Okay. Take the handle off then.
Yeah. So it does depend on where you are, of course. So I haven't run into too many places lately that anybody is talking about not allowing that in.
Okay, fair enough.
We can have long discussions on codes. I got stories for you, man. All right. Yeah. Rich says easier to ask forgiveness than permission. There you go.
Not when it comes to your inspector.
No.
Don't do that, because that's just more work for every job thereafter.
I have another question.
If we have any inspectors on here,
we love you. We love you. You're underloved and underappreciated.
Well, that just means they're coming here to learn some stuff too. That's
exactly.
That's why. Yes, definitely. They are getting smarter and they are learning. That's right, Rich.
Yeah, that's important. All right. Another question for the group out there. Expansion tanks come charged from the factory to 12 psi. Pressure reducing valves come preset from the factory to 12 psi. Why? What is so magical about that number 12? Even I know one, it was Tom Brady's number, and Tom Brady brought me more joy than any living human being in this life. I wouldn't say
Wow.
that too loud. What 12 psi. Why 12 psi? Why 12 psi? Yeah, Rich says, yeah, tell us and leave Brady out of it. Why 12 psi? Well, we learned this day one of plumbing school when I was getting my license. Day one of school, they taught us that a column of water 28 inches high would have a gauge pressure at the bottom of 1 psi, right? So 28 inches tall, it doesn't matter how big around it is, just how tall it is, 28 inches high, I'll have a gauge pressure at the bottom of 1 psi. Another way of saying 28 inches is 2.31 feet. 2.31 feet. All right. Now, if I were to multiply 2.31 feet per psi times 12 psi, the psi's would cancel out and I'd come up with 27.72 feet. 12 psi is the amount of pressure needed to raise a column of water 27.72 feet. What does that mean in our world? Well, that's enough pressure to fill and pressurize a hydronic system up to the radiation level on the uppermost floor of a normal, keyword here, normal residential structure. Let's take a look. Let's say I've got this little 3-story house here. Okay, little 3-story house. From the boiler to the first floor is 5 feet. From the boiler level there, the water level, pressure level. From the first floor to the second floor to the radiation level of the second floor is 9 feet. From that to up to the third floor is another 9 feet. 9 and 9 and 8 are 18. 18 and 5 is 23 feet. 23 in virtually every instance is less than 27.72 feet. All right. Somebody argue with me on that one. 27.72 feet is more than 23 feet. So now I've got enough pressure to fill and pressurize up to that radiation level on the lowest level with a little bit left over for safety. That's why 12. Now, if you need to go higher for whatever reason, okay, or you need more pressure for whatever reason, you adjust the pressure reducing valve to the pressure that you want. But whatever you do to the pressure reducing valve, you must also do to the air side of the expansion tank. So if you adjust the fill pressure to 15, you got to adjust the air pressure on the expansion tank to 15 as well. And you can't do that when there's water pressure on the other side. That's why, again, those valves are very helpful, or do it before you install it. So that's the whole 12 story. That's the whole 12 story. Real quick, before we get to our trivia question, I want to talk about air elimination. All right, air elimination, and just two basic forms of air elimination. We have the 4900 series air separator, and then our old friend on the right, the air scoop. The air scoop. All right. Understand why we want to get rid of air. Air is bad. We want to control air because air is bad. If you got to breathe, air is your friend. Okay, I get that. But in hydronics, air is bad for a lot of reasons. Number one, it's an insulator, okay? It's an insulator. The specific heat of water is 1. The specific heat of air is 0.24. That would be less, okay? Air doesn't conduct heat as well. In fact, it's a better insulator than it is a conductor of heat, all right? Number 2, if you combine water with ferrous metals and air, what do we get? Water plus ferrous metals plus air is going to equal something that never sleeps. Yes, rust. Matt's got it. Rust. Rust never sleeps. We got Neil Young fans out there. I love it. I love it. Rust never sleeps. Absolutely. Absolutely. Another one is circulators are really good at pumping water and moving water. They can't move air. They don't move air very well. You can always tell when you have air in that thing. It goes, it doesn't do very good. All right. Why? Here's a question. Air elimination always should go on the supply side of the boiler. Any guesses as to why? This has to do with Henry's law. Henry's law. And Henry's law states as water temperature goes up, that water is less able to keep entrained air entrained. It's like when you're boiling water, as it gets hotter and hotter, it doesn't do nothing. Then it starts to get those little bubblets on the bottom, and then it starts to bubble, bubble, bubble. All right. It's getting hotter. It can't keep that entrained air in solution. All right. So when we remove air on the supply where the water is the hottest, that's the point in the system. That's the one point in the system where the air wants to get out the mostest. So let's not fight nature. Let's let the air get out where it wants to get out. Put that thing on the supply. Okay. Put that thing on the supply. Now, talk about the air scoop. People hate these things. They love them. People love them because they're cheap. They hate them because they think they don't work. In fact, they do, and they do work very well. They just have to be installed properly. I love air scoops for some simple reasons. The most basic reason is it's basic and simple. All right. You got the gazinta. You got an arrow telling you what direction the water's supposed to go, and you infer that the other side's the gazouta. Okay. These things are very simple. When you install them, you want to be able to read the writing on the side of it without contorting your body. So it has to be horizontal. You don't want it upside down. You want it right side up. You have it upside down, and I've seen them installed upside down. It doesn't do anything for air removal. It's just an expensive coupling. All right. I've seen them piped vertically. It doesn't do anything. It's just an expensive coupling. You got to pipe them up like so. All right. There are no moving parts inside. So again, super simple. What it is, it's a big open space in the piping. Let's go back to that velocity discussion we had earlier. We want that water to slow down its velocity to less than 2 feet per second. What happens when that water velocity drops to less than 2 feet per second? Well, that's when dissolved air wants to come out of solution. Well, where do we want it to come out of solution? In the air letter outer. Okay, pretty simple. So we slow it down and it comes out of solution. So here's a little side shot of it. Okay, so water enters the scoop. That increased cross-sectional area inside, it slows the velocity down to less than 2 feet per second. The little bubblets start to come out of solution, right? And these turning vanes inside literally scoop those bubbles out of the flow, channel them into the upper chamber of the air scoop, and then right out the quick vent connected up on top. But these are very, very important. This little one right here, 18 inches of straight pipe. This isn't negotiable or advisable. If you want this thing to do a damn thing, you got to do this. All right.
It is a minimum. Remember, it's a minimum, not
a minimum, not
minimum.
A goal. Yeah, it's a minimum. You can go more. A minimum of 18 inches of straight uninterrupted pipe. No fittings or anything, straight uninterrupted pipe, creating laminar flow on the gazinta side of this thing. Think about what happens. The water comes out of the boiler, hits an elbow, flow gets all turbulated, and all of the dissolved water oxygen molecules get all mixed up. All right. Then it gets into that horizontal piece of pipe. It needs at least 1.5 feet for those lighter than water air molecules to work their way up towards the top of the pipe, so that when they enter this thing and turn back into bubbles because the velocity slowed down, the scoop can actually get at them. All right. Now, that said, how many of you have seen these things installed with, I don't know, a close nipple or a street 90?
Street elbow. Yeah, street 90.
Yeah. At that point, they're expensive couplings. They're not doing anything. People say, damn things don't work. No, they work and work great. You got to install them.
It'll hold the expansion tank for you.
It'll hold, but not with a close cut, not with a street elbow. There's not enough room.
Not straight on. Yeah, you got to put a little elbow. You got to put some work into it. Yeah.
There you go. But if you turn it upside down, then we got plenty of room for the expansion tank.
Sideways, come straight out at you. Yeah.
There you go. Don't do that, people. Don't do that. All right, 4900. This is our high performance air removal system. This is actually the best on the market for several reasons. Number one, it just removes a metric crap ton of air and air and mini bubbles and micro bubbles and mini micro bubbles and all that crazy stuff. So high performance air removal. Two things: no minimum pipe run needed here. Do not need the 18 inches. Not necessary. What does that mean? That means you don't need 18 inches. Okay, you don't need that pipe run, that straight pipe run. I'm saying this 3 times because in other classes I've said it 3 times and people still say, "Do I need that minimum pipe run?" No, you don't. No minimum pipe run needed. Okay. The magic sauce here are these little pawl rings, these stainless steel computer designed pawl rings. They're a little medium in there that when the water enters this chamber and the velocity slows down, these bubbles and mini micro bubbles and mini micro bubbles kind of glom onto these pawl rings that are three-dimensional. There's a lot of surface area in there. They glom on, and as they get bigger and bigger and bigger, they eventually go glug, 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 right up into that upper portion, that conical shaped upper portion, which is important because it reduces the likelihood of fouling that mechanism. Enough air gets up there, pushes the float down, opens up the valve, and out she goes. This will remove air faster than you can put it in, all right? Faster than you can put it in. So that pawl ring technology is coalescent medium is very important. Tested independently, and it was found because of the surface area of those pawl rings, it removes 3 times more air and microbubbles and mini microbubbles than, say, a spirovent. And the secret sauce is simply in the pawl rings. There's 3 times more surface area to get that job done. So as a spirovent is very good, this thing is very, 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 very good. Okay, in terms of getting rid of air. And the top part is serviceable as well. All righty, trivia time. We're really cruising. My God.
Hey, before you do trivia, you don't have to go back a few slides, John, but in the interest of my continual learning, we were talking about minimum maximum flow rates through given size of pipe, and there was an overlap between the 4 and the 9 GPM, and I don't think I've ever noticed that before.
There is.
Enlighten me on that.
Thank you for the reminder, Jason. That's very good. I mentioned that. I said I'd explain it later, but I skipped right over it. The reason there's an overlap, it has to do with the difference between copper and black iron.
The wall thickness.
The wall thickness. There you go. They're the same outside diameter, but copper has a thinner ID. Black iron has a thicker ID. So I'm really limited to 8 gallons a minute through 1-inch black iron. I can go up to 9 gallons a minute with no problem with copper.
And again,
thank you, John.
General guidelines.
Guidelines.
You can push the limits on either side.
Can we push the limits a little bit here and there?
Hey,
of course.
Yeah, no one's going to call home and say, "Dude, you're running 8.5 gallons a minute."
Yeah. The pipe police won't come and take you away.
Yeah.
All right, folks. Trivia time. And this has to do with Cream and our song of the night, Strange Brew. So that was one of Cream's biggest hits, Strange Brew, and it came out in 1967. 16 years later, a movie of the same name was released. A movie called Strange Brew was released. Had nothing to do with Cream whatsoever. Nothing to do with Cream. I'm not even sure if the music was in it, or it might have been. I don't know. But 16 years later, a movie of the same name was released. What comedy duo starred in that movie, and what was the name of the brewery?
A two-parter.
Two-parter. What comedy
duo? I loved this movie.
Yeah, what comedy duo starred, and what was the name of the brewery? There we go. I just want to take this opportunity to just remind you of TACO's Contractor Rewards Program. It's a points program for frequent buyers, and TACO is part of a consortium of other manufacturers. So it's not just TACO, it's TACO plus a bunch of other things. You get points for the TACO stuff you buy, okay? You get points for the TACO stuff you buy, plus all the other stuff you buy through this company, and you can redeem those things for a ship, all right? You get enough points, you can own that ship, or a toolbox or something. You can't own the ship. I'm kidding, but you know what I mean. But you just redeem the points for valuable prizes. There we go. Here are some of the other companies involved. Some of them have nothing to do with the piping trades and the mechanical trades, but many of them do. You got A.O. Smith, you have State Water Heaters, Zoller, okay, TACO. You're going to find Uponor is in there now as well. So these are all pretty cool things. You can work with. You can buy this stuff. Take a picture of your receipts through an app, upload it, and you get your points. And then you can redeem them for whatever you want. And if you want to hit that QR code, I'll leave it there for a second. That'll get you some bonus points when you sign up. So it's a great program, and it's free. Hey, who doesn't like free, right? Who doesn't like free? Zudite. Yes, a Canadian classic, says Dave. There you go. All righty. So let's get back to work and start jamming with the boys. Let's finish up with a discussion on pumping away. Where does the circulator go? Does it go on the supply? Does it go on the return? All right. Does it go on the supply? Does it go on the return? These are great questions. I would say, what is it, Dave? Maybe every week and a half, this pops up on like the boiler guys on Facebook and all that. And you got, it's a controversial question. You know, where does it go? Where does it belong? We hear from people that say, if you put it on the return, it's wrong and you're an idiot. Okay. Or you put it on the return, the system won't work. Boy, I don't know about you, but I've grown up, maybe I'm showing my age, but I've seen thousands and thousands of hydronic heating systems with circulators on the return side that work just fine. Why is that? Why is that? Interesting. Why is that? If putting it on the supply is right, then the opposite must be wrong. Why is it wrong? It's not. People just get very upset, very, adamant. Got to pump on the supply. Do it right. Put it on the pump on the supply. Do it right. Put the pump on the supply. But why did all these systems work with the pump on the return? Interesting question. Interesting question. There are compelling reasons for pumping away, not from the boiler, but from the point of no pressure change. The point of no pressure change is this spot right here where the expansion tank connects to the boiler. That's called the point of no pressure change. Why is it called the point of no pressure change? Why is it called the point of no pressure change? If you're going to go to all the trouble of calling the point of no pressure change the point of no pressure change, Jason, I'll ask you, isn't it easy to presume then, if something's called the point of no pressure change, that the pressure doesn't change at the point of no pressure change? Does that make sense?
It's easy to presume that, yes, Chuck.
It's easy to presume that. If you're going to call something the point of no pressure change, you can presume that the pressure at the point of no pressure change won't change, because why else would you call the point of no pressure change the point of no pressure change? That makes no sense. I will suggest to you, however, my friends, that the pressure at the point of no pressure change does change, and it changes all the time. Yes, the pressure at the point of no pressure change does change, and it changes all the time. If that is in fact the case, why then would you call the point of no pressure change the point of no pressure change? If the pressure changes at the point of no pressure change, how can you call it the point of no pressure change?
That's insane.
It's crazy. Next thing you know, dogs and cats are going to be playing together. What's going on? What's going on? Well, there's a reason the pressure changes at the point of no pressure change, but none of them have anything to do with the circulator. The reason the point of no pressure change is called the point of no pressure change is because it's the one place in the system. I'm going to say this again. It's the one place in the system where the circulator can't change the pressure. It's the one place in the system where the circulator can't change the pressure. Circulators, we call them pumps, but they're really circulators. In fact, better name for it is they are actually pressure differential machines. Their job is to create a pressure differential. What comes out, that comes in, goes out at a higher pressure. Okay, changes, it's a pressure differential machine. That's all it is, okay? But let's take a look at the things that can change the pressure at the point of no pressure change. One thing that'll change the pressure at the point of no pressure change, you heat up the water, what happens to its volume? All the molecules get all higgledy-piggledy, and the water becomes less dense and higgledy-piggledy. Jason, write that one down. That's also that's a technical term.
Two G's?
In both, yes. You heat up the water so it expands, it becomes less dense. Its volume expands, and it expands into the expansion tank. You put more water in the expansion tank, you compress the air, the pressure in the system goes up. Pressure, the point of no pressure change goes up. You could also, now the circulator doesn't heat up the water so it expands. That's the boiler's job. The boiler's doing that. The circulator's not doing that. The circulator has nothing to do with that. Secondly, you could add or remove air from the air side of the expansion tank. Well, the circulator obviously can't do that. It doesn't know how Schrader valves work. And even if it did, it doesn't have hands and arms. It couldn't reach it. So the circulator cannot add or remove air from the expansion tank, which would also change the pressure at the point of no pressure change. And lastly, you could add or remove water from the system / expansion tank. You could put more water into the expansion tank, take more water out of the expansion tank. The circulator can't do either one of those, either. Okay, circulator can't do those. As far as the point of no pressure change is concerned, the circulator doesn't change the pressure. It can't. Only those three things can. Let's take a look at this in a little closer detail. An expansion tank, how does it work? You take it out of the box, you look in that little hole there, and you can push your finger in and you can actually touch the air cushions. It's all air, no water. All right. You spin this thing on, you fill it up, you put some water in. Okay. You're pushing down on it a little bit, the air's pushing back, and you got your 12 psi static fill pressure. As the water heats up and expands, it pushes into that expansion. I guess that's the only place it can go, because that's the only place with any give. All right, it pushes that cushion, that diaphragm down. The volume of air gets smaller, the pressure then goes up, and that is Boyle's law. Okay, so the lower the volume of the air, higher pressure. The lower the pressure, the higher the volume of air. Okay, so that's kind of how that works. Now, let's take a look. I am circulating into the point of no pressure change. All right. So my water flow direction is this away. All right. While this is happening, while the circulator is pumpulating this way, could this circulator be so humongously big that while it's doing that, it's also jamming more water down into here, changing the pressure at the point of no pressure change? Could it also be so powerful that you can jam more water, pump more water into the expansion tank, thereby changing the pressure at the point of no pressure change? That's a question for the group. Can that actually happen? Can that circulator be so big and so powerful that it can push that water into that expansion tank? All right. What do you think? I got a nope. I get a negative. I get some yeses, and I get some no's. It's either one or the other. It's either yes or no. There's no third answer. But the answer is no, it can't. In order, remember, we're talking about a closed loop system, my friends. We're talking about a closed loop system. In order for that circulator to do what you think, to actually pump more water into that expansion tank, where would it come from? It has to come from somewhere. I have a fixed amount of water in this system. All right. I'm circulating water through the loop. In order for that circulator to also take some, I get some extra water here. I'm going to shove it down that hole and into the expansion tank. Where's that water coming from, man? You can't, and if it could, what would it leave behind? It can't leave behind a vacuum. There's no air. You can't have a vacuum unless you start with air, right? So it's not leaving a vacuum or anything. It can't be done. It cannot push more water into that tank, because circulators don't push. They don't pull, they don't lift, they don't separate, they do any of that stuff. Circulators circulate. They create a pressure differential. High pressure goes to low pressure. Mother Nature takes over. All right, that's what they do. So in this case, no, it cannot push more water into that expansion tank, because there's no water to push. It can't do it. All right. What if I moved it on the other side, and I got this big honking circulator, and I'm circulating through the loop? Could the reverse happen? Could, by some Venturi effect, could I pull water out of that expansion tank and add it to the system? Could that happen? Well, again, there's a no for the exact same reason. Where would you put it? Yeah, there's no room. Dave's got it right. There's no room. You can't compress water. Okay, there's no room for that extra water. So as far as the expansion tank is concerned, it is the one spot in the system where the circulator cannot change the pressure. That's part one of understanding pumping away. Here's part two. So let's say I have the circulator on the Gazinta side. I'm pumping into the point of no pressure change. All right, I'm going into the point of no pressure change. So right now the circulator's off. It's not doing anything. There's no pressure differential. Okay, I've got 12 psi at the tank. Now, if I had pressure gauges, and let's say these gauges are at the same level as the tank, everything's in the same level. I got gauges on the Gazinta and the Gazauta side of the pump. Both of those gauges at this point would read 12 psi, right? Because that's at the bottom. It's at the bottom of the loop. Everything's at same pressure right there at the bottom. It's all at the same level. So 12, 12, and 12. It's not doing anything. It's just reading 12 psi. All right. Now, remember, 1 psi for every 2.31 feet. All right, 1 psi for every 2.31 feet. The highest point in our system is 18.5 feet above this point. 18.5 feet. If you divide 18.5 by 2.31, you're going to find that there's about an 8 psi, natural 8 psi static pressure drop or pressure loss, not in terms of head loss, but just there's going to be an 8 psi lower pressure at the top than there is at the bottom. Okay, an 8 psi lower pressure at the top than is bottom, and that's just nature, that's just gravity. Okay, so way up at the highest point, if I had a pressure gauge up there, it would read 4 psi. All right, 12 at the bottom, 4 up at the top. That's just height. Okay, now let's turn this circulator on. 12 psi at the tank. I've got 12 psi at the outlet. The circulator is capable of creating a 4 psi pressure differential. 4 psi pressure differential. I can't raise the pressure going into the point of no pressure change because I can't change the pressure there. The circulator has to create a pressure differential. It's not that it creates a pressure, it creates a pressure differential. All right. I can't go higher than 12. What I can do is have 8 on the Gazinda side. It's the coolest thing you ever saw. If you've never seen it, we have a demo unit at the factory that'll show this. Both pumps are off. The gauges are like this. All right.
I
this
got,
is the
I got a
gauge
video that I want to show later on, JB.
Okay, cool. And you can just see the Gazinda gauge drop. It's the coolest thing. It's like I've had guys say, "Oh, you're gonna have to prove it to me." So I don't have to prove it. I didn't make it up. This goes back to the 30s, right? Bam. The Gazinda gauge will drop, and it's pretty slick. All right. So in this case, it's 8 psi or 4 psi lower. Now, if we follow the logic here, if it's 4 psi lower right here, okay, how about up here? It's also going to be 4 psi lower. And if that was at 4 psi earlier, now it's at 0 psi. Now, this is why you want to pump away, because you don't want this to happen. All right. If I have 0 psi up there at that high point, if I have no psi, I can't have a pressure differential. If I don't have a pressure differential, I don't have flow. If I don't have flow, I don't have heat. If I don't have heat, I don't have a happy customer. All right. So this is what we call a no flow situation. Even though the circulator's working, the boiler's working, for some reason, I'm not getting flow. I'm not getting heat. The most obvious conclusion when you go to troubleshoot something like this is, okay, the pump's pumpulating, the boiler's boilerating, but I ain't heaterating. What's going on? You put your hand on the Gazinda side of the pipe and it's cold. You put the hand on the other side of the pipe and it's hot. And you go, huh, I know what that is. That's airbound. That's what an airbound loop feels like. I know I can fix this. That's an airbound loop. You put your hose on it. You purge it out. You bleed it out. Cold water comes out, but in a matter of a few seconds, you start to get hot water. You say, by Glorioski, I must have fixed it. But what didn't come out of that hose? Air didn't come out of the hose. You didn't have any air, right? You didn't have any air. If you don't have air, you don't have an air problem. You had a flow problem, all right? You had a flow problem. So that's the problem here. That's the problem that you can have here. Now, why did systems work for so long like set up like this? It has to do with this guy right here, the 4 psi pressure differential. Okay, that's about 9 foot ahead. All right, 9+ foot ahead. You go back to the old circulators, that makes an old B&G 100 or Taco 110, about 2 or 3 feet ahead, 4 feet ahead. Low head pumps. The pressure differential was lower back in those days, and this would work just fine. You'd never have a problem. It would work and work just fine. The problem started to creep up when those circulators finally died and we had to replace them. And what did we replace them with? Well, we replaced them with 3-speed pumps because somebody somewhere said, yeah, I put in a 3-speed pump for service. It's the only pump you'll ever need. Completely different pump. It's a steep curve pump. It's a high head pump. You're putting a high head pump in where a low head pump belongs, and you create a problem where there was none. All right, we create a problem where there was none. Now, what do we do to fix this? Well, we could raise the pressure, right? We could raise the system pressure, and we'd have to raise the pressure in the expansion tank. But the question is, by how much? We're kind of guessing, right? We're kind of guessing. And if you do it and it's not enough, then you got to do it again. If there's no valve on that expansion tank, you got to drain the system, add air to the expansion tank, and start again and see where you're at. It's not a certain solution. It's not a certain solution. You could also, well, I've got to put the pump on the supply side. Well, yeah, that'll do it. But why would if the system worked for decades with the pump on the return, why would I repipe the system? That makes no sense whatsoever. Why would I repipe the system just to move the pump on to pump away when it worked for generations with the pump on the return? The answer is if that pump's on the return side and it worked forever, there's a reason. And the reason was it was a low head pump. You got to put in another low head pump. All right. 0015E3, our ECM circulator at low setting, 5 foot ahead, working here just fine. It'll work here just fine forever. And it'll give you the flow you need. So, right. Now, if we were to pump away, and if you're building something, if you're replacing a boiler and building a new pump tree or starting new, pump away. It just saves a lot of problems. Pump away. It's the right thing to do. Okay, it works. It works. It saves you issues. You'll have very little air issue, and you'll always have flow. So there's no reason not to do it that way. But in this case, everything's off, like we said before. Okay, and our 4 psi up top. But we turn it on. Now, I'm adding the circulator's pressure differential. Higher pressure, it's going to keep dissolved gases dissolved in the fluid longer and better. Okay, so think about this. Water's the hottest, air wants to get out the most. That's where we have the air letter out, or the air separator, right? Immediately after that, we add extra pressure to the fluid. Whatever's left, goes right back in solution, and it stays in solution for the entire journey around the system. So that's why pumping away is a good idea. Having the pump on the return side is not wrong. All these guys for generations, they weren't wrong. Okay, they weren't wrong. It's just that when you replace that circulator on the return side, make sure you replace it with the right kind of circulator. All right, cool. And again, what we're talking about here is Henry's law in terms of pressure and keeping dissolved gases dissolved. All righty. I'm sorry, I went 11 minutes over, Dave and Jason.
No, it's all about the laws. It's all about the laws.
The laws,
Hey,
and it's
before, I don't know if you want to do the trivia answer first, or you want me to show the video.
Let's do the trivia answer first because I got it teed up. Then we'll go to the video.
True that. Yeah, yeah. How do you keep an idiot in suspense? I'll tell you tomorrow. So right. Yeah, let's
So our Takeo trivia answer. A lot of you guys got it. It was Strange Brew with Bob and Doug McKenzie. All right, the Canadian duo, Rick Moranis Rick Moranis and Dave Thomas. Great movie. One of just a funny one. Hosehead the dog was my favorite character. And it was the Elsinore Brewery. The Elsinore Brewery.
Very good.
Yeah. What a great movie. What a great movie. So anyway, I know we got a lot of correct mundo answers in there, and Dave, I'm sure you got them on the list now. What's up next week? Flow, head, and the finer points of circulator selection. That one's going to be fun. And
so Dave, you know what's going to be fun about that one, JB?
What's going to be fun about that one?
The three of us are going to be together in Rhode Island.
Oh man,
that is correct. Yes.
Recipe for disaster.
No way, man. It's going to be the three caballeros together live in the same room next week.
So at the factory last year, you and I had planned this class to be when we did this one in Rhode Island. So we had the pumping away display.
Yeah, that's right.
There at the factory. So last year it was planned. So next week is the factory class. So for those of you that are not sure, we do basically Takeaway After Dark live in Rhode Island for 2 days. It does start next week, Thursday, Friday. If you're interested, there's still a few spots open. I know I was talking to Jackie earlier today, my coordinator takes care of everything, and we still have spots. So if you want to come to Rhode Island, hang out with the three of us, Thursday, Friday next week is when that is. Anyways, so cool. Sorry, I went on a side tangent there.
That's all right. Dave. That's your middle name. Go off on a side tangent. Dave, go off on a side tangent. Holbdorf. Anyway, all right, Dave. I'm going to turn this over to you for your video and the winners. So.
All righty. Hang on 1 second.
Oh, you've taken the con.
I already took it from you. That's right.
There you go. Now you got to share your screen.
All right. Wow. Yeah, lots of names tonight. Lots of names tonight. And hey, everybody, I know for those of you that have been to the last several classes, and I've got all your names actually written right here. Guess where I am the rest of this week? In the home office. I will actually be home the rest of this week, and that's on my goal for tomorrow to get everything shipped out of here. I got a ton of stuff in the basement. So yes, I know Yvonne, who won first week. We got Vincent, who won the second week. And tonight, let's go see who wins. Shall we?
Hit that wheel, baby.
All righty. Sorry, I got some stuff in the way here. All right. Click on that wheel, and let's get that little bit of Strange Brew growing. And it looks like, wow, Mr. McGrath, of course, has won so many times in the past, but this is the backpack cooler grand prize. Good job, Mr. McGrath.
All righty, Rich.
All right, I've got a few t-shirts to give away too, some Takeaway After Dark t-shirts. Let's see, what do we got? And the Elsinore Brewery wins. All right, so we'll get rid of that one. Ashley, excellent. Thank you so much, Ashley. Greatly appreciate it. Let's see who else. So we McGrath, Ashley, and Kevin is winning a shirt as well.
All right.
Yep, I will make sure I get this stuff out. I've got all your addresses and everything else in there. And you know what? Just because.
One more.
One more.
One more because.
Just
Mr.
because.
Tossie.
Toss. All right, Anthony.
All righty. Yes, Mr. Tossie joined us this evening. Good to see you guys. All right, everybody. I do want to say thanks for joining us tonight. Actually, don't leave yet because I do want to show you that video
I
of.
want to see it.
Yeah, so we did the Takeaway After Dark. This is first season or first year that we did Takeaway After Dark back in 2020. That I have all queued up the video for us. So this was this session that we did back in 2020. I had this display. I built this display. And what you've got here, before I get into the description of what's going on here, so you'll see that we have a 006 E3 circulator. So kind of a steep slash flat curve. It's in the middle. It's a fleet curve pump, as John likes to call it. Yeah.
It's a fleep. Yes. Not flat, not steep. It's fleep.
Right. So I've got a pressure gauge on either side here, and it is pumping in the direction to the left, and it goes up, and you'll see there's a cross here with an expansion tank on it, and we have a valve on either side of the tank. Comes up, we hit a globe valve, and I only added the globe valve just to give it some pressure drop to it. And you see I've got an air elimination. That was just so I can help get the air out of the system itself. Comes down, there's a little drain valve, and it comes back again. So when I start off right now, you'll see this blue valve is open, the yellow valve is closed. So what you'll see there when I start this video, also notice the pressure gauges. All right, and what you see on the pressure gauges here, let's see, are we running? Is it moving? It's moving. All right, I'm talking in the background here, telling what we got going on. And you'll see the gauges. They're both of them around 20 PSI. The pump is off at the moment. All right, we've got about 20, 21 PSI in there. And we're going to go bang this pump on. And as we turn that circulator on, you're going to notice that the discharge side of the gauge is not going to change.
Nice ascot.
You like that? Yes, that was season 1 when we had an ascot. And if you haven't seen the ascot, we had some fun during Takeaway After Dark.
Yeah, we did.
As anybody did in 2020 during COVID. You know, I'm not even in the studio office that I'm in now. This is down in the basement. You know, so this when I did this video, it was about 60 degrees down there. So yeah. All right, so let's kick this thing on. Come on now, Dave. Turn it on. Turn it on. No. Don't point anymore.
Yep, the other way. The other way.
Yes, quarantinis. Yes, there's a lot. I was enjoying a lot of drinks and seeing what ascot I can get on Amazon quickly.
There we go. We just turned it on. Watch that.
Not yet. We don't have the blue light on. So I was just talking about where the gauges are set, and they're about 1 PSI off. They're not exactly the same. So here we go. We're going to kick the gauge on, the circulator on. 1, 2, 3, go, Dave. I can't trust this guy. It's only about a 3.5 minute video, so I went through a little description beforehand, so I apologize. I should have started it sooner. There we go. Pump is running.
There we go.
And you'll watch those pressure gauges move. One of them stays the same. One's going to remove. So discharge side stays the same as we expected and as we talked about. But now you look at the suction side and you can see it dropped.
All right, so you're pumping.
I'm pumping into the
expansion tank. Look at that.
The blue valve is open here. Yes.
Yeah, so Dave, so I see what you built here. So if you close the blue valve and open the yellow handled valve, that just basically switches the
exactly.
flow.
It switches it around. So now it makes the expansion tank on the suction side of the circulator. And here we go. So we're going to see that example now as we flip it over. Now, both, again, gauges went back to the same. You know, they're slightly off because these were gauges that were shipped in a box for a long time. But now you'll see the discharge side change, goes all the way up to like 22 PSI, and the suction side remained the same.
Wow.
Right?
That's pretty graphic. That's pretty graphic.
Yeah. So I remember building this in the garage. I had a contractor friend of mine come over at the same time where we're wearing masks. I mean, I've known this guy for 10 years and we're wearing masks, you know, which is just, oh God, I don't miss those days whatsoever.
No, definitely not.
Yeah, no.
How about that? That's a graphic illustration of what happens. Now, again, when we're going to talk about this again next week, is the high head pumps on the return, really bad idea. Okay. Flat curve pumps, you know, I'm going to say steep curve, high head, steep curve pumps. You know, the Takeo 3-speed, the standard efficiency 0015, 3 steep curves. Grundfos 1558, 3 steep curves. Okay. It's a European style curve, low flow, high head, steep curve, because that's kind of a European style system. You look at, say, you know, a standard Takeo 007 is a flatter curve, high flow, relatively low head, flat curve. You go back to the B&G 100, Takeo 110, those go out to 30 gallons a minute, but they may max out at about 5 foot ahead. Talk about the ultimate flat curve pump, perfect circulator for those types of applications. You start putting a steep curve pump where you need a flat curve pump, then these are the kinds of things that you're going to encounter. The guys in our tech services department say that is one of the more common phone calls that they get, that you know, it's when combine a steep curve pump with zone valves. A lot of times that's when you get banging zone valves. That's another concern. But steep curve pumps on the return side of older systems, all of a sudden you got a no flow system. One of the more common phone calls they get. And I said, well, you get the wrong pump there, man. I mean, you could boost the water pressure, and that in theory should do it, but I don't know what pressure is right and what pressure is going to be too much. And if you don't have a gauge like that 3450, you know, that'll tell you what you set at, you're pretty much guessing. All right, you're pretty much guessing, and you want to, if you want a sure solution, is take the wrong, we call the hydronics hokey pokey. You know what the hydronics hokey pokey is, Jason?
No, I do not. I haven't heard this one.
You take the wrong pump out, you put the right pump in, and you shake it all about.
Well, remember you said none of us are good singers, so isn't the pumps being mounted on the return, or on the return, isn't that sort of a legacy of like older pump mounted boilers where it was just on the return? Like,
there's a long history there. Let's go back to the 1930s, my boy. When Homer Thrush invented the first centrifugal pump here in North America, those days the pumps were they put the circulating pumps on the supply because they work better, you know, pumping away from the point of no pressure. Everybody knew that was the right way to do. The problem was they were using seals for those pumps that were, you know, made out of leather, that kind of thing.
The three-piece.
High temperature would cause those things to leak after a while. And it was a kind of a pretty big problem. And they said, what are we going to do? We said, well, we could either dedicate millions of dollars in research to develop a special material for our seals that could resist these high temperatures. It's the right thing to do. It pushes science forward. It's good for the industry. We could do that. And I could just imagine some sales guy in the back saying, just move the pump to the return side. The water's cooler there. You'll be fine. You know, and that's kind of what they did. They said, put it over there. The water's cooler. Problem solved. Then when they started selling packaged boilers, you know, these would be old knockdown boilers. When they started selling packaged boilers, you know, habits died hard, and it was also easier to crate and ship these things with the pump mounted on the return side. All right.
Right. And you also start thinking of that pump also, you know, about this long, right?
Yeah.
And you never supported the motor part. You always, you know, you supported it by the pipe. And now when you had it shipped with the boiler and the return pipe, the return tapping on the boiler was down low, you put the pump on the boiler by the OEMs, right? Today we get it in a box, but you get it by the OEMs. And then that boiler went on a truck and bounced around the entire country, right? And therefore you didn't want to bend the frame that was holding the motor, so you put some blocking underneath it so you can ship it easier.
Yeah.
So it was all about just making sure you got something the way it was supposed to operate also
Right.
at the same time. Yeah. Yep.
And think about the systems installed in the 50s, 40s, 50s, 60s. They'd be, big pipe, high flow, big pipes installed while the house is being built, low head. I tell the B&G 100 or Takeo 110, perfect pump for that. High flow, low head, flat curve, piece of cake. As systems evolved a little bit, as we started getting into radiant floor heating and situations where you might need a little bit higher head pump, and now you came out with those 3-speed pumps that everybody's, oh, that's the only pump I'll ever need. It's got 3 speeds. It's the truck you put on a truck for service. Where do people, when anybody uses a 3-speed pump, where do they set it? Nobody thinks this through. You put it on contractor no callback mode and get the hell out of there. Well, now you've just installed the time bomb, if you will. It's a high head pump where you need a low head pump. You create too much pressure differential. You wind up in that possible no heat situation. And then how do you figure that out? Then you go through all these histrionics to try to figure it out. You wind up I got to put the pump on the supply side. Well, then you're rebuilding a system that worked fine for generations. That makes 0 sense.
Right.
0 sense. Take the wrong pump out, put the right pump in, and you shake it all about, and you do the hokey pokey. And that,
we'll see a lot of that
is what it's all about.
Next week's class, definitely, right? So when we start really analyzing curves and stuff like that, we'll see that next week, a big time. Yep.
There you go.
Awesome, guys.
Hotter water has a higher output in screw delta T. There you go, Richard. I love you, man.
Yeah, good to go.
Rich McGrath might be one of my 3 favorite human beings on the planet. I love you, man. Who am I? I know who you are. And I know who you are mocking. I'm sorry, man.
You can't constrain it.
Jason, we have to let you in on that story at some point.
Yeah, I've got a lot. I'm sure I've got a lot of stories to catch up on.
A lot of inside baseball stuff we're going to teach you, my man.
Yep.
Man. All right.
I can't wait.
All right. We've still got 42 people out, 40 plus people out there. God, that's great. What questions do any of you guys have before we say goodnight? What questions might you have? Is it the physical size of the commercial pump that can cause cavitation? Physical size and horsepower. Yeah, it required.
Bigger, obviously, the horsepower gets bigger, so that's what does it. Yeah.
Yeah, and the required net positive suction head that circulator needs, those pumps need to get in.
This little thing, 1/25th, not very strong. I can stop it with my finger. Yeah.
And that's what causes. And cavitation is basically low pressure on the inlet side. Let's see, what happens is basically you create little implosions of dissolved oxygen. These things will kind of beat up and then they implode because of pressure, kind of like the submarine. Remember that submarine that went down and it was going to look at the Titanic? It imploded. It's the same kind of concept. These things will implode and they'll cause these little, I got explosions, but they're implosions inside the system right on the impeller. And it makes a hell of a racket. It sounds like there's marbles in there, right?
Yeah.
It sounds like there's marbles and things inside. And it makes a hell of a racket. The good news is it doesn't last very long. That you let it go, that noise will go away. The problem is, so will the impeller. Okay, the impeller will go away too, but you won't have any noise. That's the good news. So yeah, it sounds like rocks. Yeah, it sounds like rocks or marbles. Yeah, it sounds like gravel in there. It's kind of crazy. All righty. We got an extra large tall shirt for James Winslow. Did James win tonight? I don't remember. Did James win tonight? Or is he just fishing for a shirt?
He wants to know where you can buy a hat too.
Oh, where you can buy a hat? Not like this one. This one I got at Shingle Creek in Orlando.
Where you at, Mr. James? I'm not sure where you're at. Let me know where you're at, brother. Just curious. I mean, I got your address anyway. I'll go look it up myself. Just curious where you're hanging. So I have limited supplies of stuff here. So Michigan. All right. Okay.
All right. Lincoln Park, Michigan.
I did.
All right. Well, if we get any more questions, guys, throw them out there. We had one on cavitation, so I appreciate that. Where can I purchase a hat? We don't really sell hats. We should have a boutique. What do you think? We have a Takeo After Dark boutique.
We did have a question before from Lewis. He was asking about venting. All right, automatic venting versus manual venting. Right, and is there a difference? He's heard this term before about different types of venting out there, and I responded to him in regards to everything is an automatic vent, meaning it's trying to pull the air out. So when you get to our basic 400 vents that you're going to see sitting on top of a basic air scoop, but very similar idea when you look at your 4900 vents. Okay, this is a reservoir that's going to collect the air. My suggestion for everybody, when you start thinking about the terms automatic and manual, automatic means you leave the cap open, and that is going to let air out of the system itself. Manual means you closed it and somebody has to let it out. So the way I like to look at using your air vents is, if you've done any major surgery, new install, things like that, I like to keep the cap open and let this automatically let the air out. But after that 1 year, the air should be out of your system. I like to keep the cap closed personally, because then if there is any air in your system, at least it's attracting in here, and therefore you come by on a yearly service, you open up the vent, you let the air out. After that first year, you should not be letting air out anymore. If you still have air coming out of the system, that means there's a leak somewhere and you're getting more water coming in. When you bring water in from the street, it has about 10% air. So you want to make sure you get that air out. And if you keep on having air, that means you need to go look for something. So when we have automatic vents always open, we may not know of problems until it's too late. That's my suggestion. When you start thinking about the difference between automatic and manual air vents.
Yeah. And so talking about coin vents, like on a cast iron radiator, you don't want to leave those open because then you just get water all over.
True that. Yeah.
But that's one other thing about cast iron radiators, very interesting point, and pumping away, is when you do pump away, you have a tendency, since you're adding all that pressure, you will obliterate a lot of the air in those cast iron radiators to the point where you may not have to vent those things. You may just obliterate them, and whatever's left comes back through the system and then out your thing. You may never have to bleed a radiator again when you pump away, which is kind of an interesting way of looking at it.
100%. Yep.
And
it depends on how much work you've done to the system. I mean, if it's drained down and it's just it depends on how it's piped in too. Yeah.
And and you think about where your liability is. It's up in the. You go open up a little key air vent on a radiator, and you get your coffee can, and you hope there's nothing in the way, and that stream of water goes right into the coffee can and not off to the side, and get the nice white carpet messy or anything like that. Those are all the problems that you might run into. And then ever open one of those things and it's really old and you try to close it and it says, I don't think so.
Yeah.
Now what the hell are you going to do? Those always keep some of those spares with you. And then how long have they been in there? Can you tap them? I don't know, man. Yeah, it's one of those things like in the Three Stooges. Remember those where Curly's pulling a thread on his coat and he's pulling it and he's pulling it. He starts pulling it, and then all of a sudden all of his clothes come off. I mean, that's just to me that's the hell that is touching old shit.
Yep.
Because everything was fine until you showed up.
Right.
Yep.
Yeah.
Like hitting the relief valve on a boiler or a water heater.
And it doesn't seat again.
Seat back. Doesn't seat back. And you're like, oh, I was just gonna get off work. I was gonna head home.
Oh, I did this once. I was replacing a boiler at my cousin's house, and I had to shut the water off because it was an old house and none of the valves were holding. So I went to go shut the water main off.
Oh no.
It was an old gate valve, and an old gate with that. You turn that and you hear that click and you go,
no. I'm here all weekend.
Oh, now they got no water.
Yep.
Oh no, I'm sorry. I couldn't turn it. That's right. I was trying to
Couldn't turn
close
it
it.
off.
I
Yeah.
couldn't turn it off. And I'm
Right.
thinking, okay, do I just take this thing off and try to cap it real quick? And no, that's pretty stupid. And I didn't do that, thankfully, but a lot of leaks. It was not a good day. It was not a good day. My cousins were not impressed with my skill.
Yeah. You love it when all of a sudden you're trying to do a favor and it just goes
Oh,
back.
yeah. It happens to the best of us, you know.
No
It's
favor,
usually
nothing. I charge them full price. Screw it.
it's the mother. It's always the mother-in-law, right?
Yeah. Yep. Whatever they say, whatever you do, don't F it up. All right, folks. I think we've had a wonderful night. And I
Yeah,
think
right.
it's time for us to bid everyone an adieu.
Adieu, hosers.
Adieu.
I had to squeak one in there, man.
There you go, man. There you go. All right, folks. Have yourselves a wonderful week, and we'll see you next week live from the factory in Cranston, Rhode Island for Takeo After Dark.
Cheers, guys.
Lay down.